So function notation. Oh, often, instead of writing y in the equation, we like to write f of x, implying or kind of showing the value of y depends on or is a function of the value of x. It's still kind of the same thing, but it has its uses. For example, if I had, say, the function y equal to 2x squared minus 3x plus 4, if I wanted to know what y was equal to when x was equal to, say, 3, it's kind of a lot of writing to do, right? I might say, okay, x equals 3, y equals 2 times 3 squared minus 3 times 3 plus 4, which ends up being 13. Alternatively, if we write the function as f of x equal to 2x squared minus 3x plus 4, it's a lot easier to contain all of that information in much less writing. Instead of writing x equals 3 and y equals whatever, I can write f of 3 equals 2 times 3 squared minus 3 times 3 plus 4, which is equal to 13. And it's just a little bit smoother, takes up less room, and it still tells us the same information. This notation here tells me the input is 3, the output is 13. Okay. Thanks. So we're going to use this notation. It's pretty standard. I imagine most of you have probably seen it before. But again, you can always think of f of x as just the y value, right? F of x is the output, x is the input. Or f, and we usually think of x being the input variable and f of x or y being the output variable. But people obviously do lots of different things. So you could use any kind of letter you want. You could have your function, you could write something as a function of A, B, C, whatever letter is suitable. T is often a choice because we input time and we get out something. So for example, last class when we were talking about like exponential growth and decay, it totally would have made sense to say something like f of t equals c to the kt, or y of t equals c to the kt. Those are perfectly normal ways of writing those functions as well. All right. Most of today's just going to be talking about some basic graphs, how they look, how we can kind of move them around a little bit. So, and these are graphs you kind of want to have, I think we call them kind of like a, I don't know, this is like your, oh, there's a word, a catalog of graphs. So these graphs we're going to see, you should kind of be like in your wheelhouse. They should be there. Be like, oh yeah, I know what this one looks like. I know what that one looks like. Because people are going to kind of say like, yeah, we know this, and then we're going to do this to it. So square root of x. Let's start here with plotting the few values. In fact, I'm going to start with some values that don't work. Square root of -4, nope, no good. Right? We can't take the square root of -4 and get a real result. The first number we can take the square root of is 0. I should say the smallest number we can take the square root of is 0. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 4. Is 2. You got it kind of in the pattern there, right? 0, 1, no, it's 2, and so on. So I'm going to plot the points 0, 0, 1, 1, 4, 2. The next nice one will be 9, 3. And the graph looks like this. There's your typical square root graph. Goes up and to the right. The domain is all x values greater than or equal to 0. The range is the same. All y values greater than or equal to 0. People like to write the domain and the range in lots of different ways. Another way of writing this is what's called interval notation, where for the domain we would say it's going to be bracket 0 to infinity with parentheses. Let's say you're starting at 0 and you're getting everything to the right. And the range would actually be the same. We don't need to worry too much about the interval notation right now, but it is a common notation. Yeah, Christian. Say it one more time.
All real numbers?
It wouldn't be all real numbers because all real, it'd be all, you could say it's all real non-negative numbers, but the real numbers also include the negatives. So, and we're not getting the negatives here. So it's not all reals. So there's a square root function. It's going to be kind of, there's not a lot else to say. It's a square root function. It looks like that. You input a number and you get out the square root of that number. That's what it does. Let's look at some more. Let's look at the absolute value function. So the absolute value takes a number and gives you the same number if the number was positive. Absolute value 4 is definitely 4. But if the input was negative, the absolute value of negative 4 is positive 4. So any positive number, I like this green pen better. The output's positive, but any negative number, the output is the same corresponding positive number. So we can plot some points. You get the point 0, 0, 1, 1, 2, 2, 3, 3. It kind of goes on. We also get the points negative 1, 1, negative 2, 2, negative 3, comma 3, etc. This is your typical absolute value function shape. People say it looks like a V, although it's kind of like V is usually like a little like narrower, but it's kind of V-shaped. This is the other function or the type function we say has a vertex. So when someone says, what's the vertex of a function? There's only really two types of functions they're talking about. It could either be a parabola, which definitely has a vertex, or it could be an absolute value function. They also have vertexes because there's kind of like a bottom point that's the center of some axis of symmetry. Other than that, we don't really talk about the vertex of a function, just for parabolas and for absolute value functions. The domain here is all real numbers, right? X can be anything that's real. So you can see that's all reals. You can also write that in interval notation as negative infinity to infinity. The parentheses on both of them because you can't actually include infinity because it's not a real number. The range, on the other hand, is not all reals. What's the lowest the y values can be here? 0. So our range is actually the same as it was before. It's y is greater than or equal to 0, or you could write it as bracket 0 to infinity. We use a bracket when we want to include a number. We use a parentheses when we want everything up to that number, but not including that. So feel free to ask questions if you got them. Nothing too exciting yet. The next one. Maybe if my thumbs were. Cubic function. We can plot some typical points. Typical x values are 0, -1, -2, +1, and +2. Y values, let's see, -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So we've got some points we can plot. I will admit before I graph this one, I'm always not great at graphing this one. So I've got 0, 0, I've got 1, 1, I've got 2, 8, I've got -1, -1, I've got -2, -8. It looks pretty extreme. It is pretty extreme. And if you graph this like using a graphing device, it's going to look like it gets super big, super fast because it does. Here's what it looks like. It's not my favorite graph to draw. When I draw this one like freehand, when I'm not trying to make it look super precise, I draw it more like it doesn't look quite as extreme as how it actually is. So the graphs don't have to look perfect, they just have to be close to the right idea. And for those of you on Zoom, hopefully you can kind of see that a little bit. That's how I kind of graph it usually. Domain. So when I think about domain, I'm really thinking about, is there anything X can't be? Is there anything X can't be? No. Domain is everything. All reals. Range, also everything. And there's no y value that you're not going to get. Unlike a square function or a quadratic function where you would be missing some y values. See, yeah, all right.
If it was negative, would it go like deadly?
Yes, this is the perfect question because it's exactly what we're talking about next. Yeah, but you're right. So if it's a negative on the outside of the function, it's going to flip it over the x-axis. So yes, a negative outside of the function flips or reflects is the more mathematical term. The function vertically across the x-axis. My favorite example of this is probably the quadratic function y equals x squared. So here's y equals x squared. It looks like this. And then y equals negative x squared, exactly. Flips it over like that. On the other hand, if you do a negative on x or a negative inside the function before you do the function, it's going to flip the function horizontally. And this is a common theme in graphing. And if you do something kind of outside of the function, it affects the function in a vertical way. Whereas if you do something inside the function, it affects it in a horizontal way. So this would flip or reflect the function horizontally across the y-axis. So here's a couple examples. We've already seen the regular square root function and the regular absolute value function. They look like that. And now we're going to do some stuff. So I'm going to graph f of x equal to negative absolute value of x. And we can plot some points in case we weren't sure. So if I'm doing x and y equal to the negative absolute value of x, now when I plug in 1 for x, I'm going to get negative 1 for y. When I plug in 2 for x, I'm going to get negative 2 for y. And if I plug in negative 1 for x, I'm still going to get negative 1 for y, because it's negative the absolute value of negative 1, which is negative 1. So no matter what the x values are, the corresponding y values are all now negative instead of all being positive. So I've got the point 0, 0, 1, negative 1, 2, negative 2, etc. And also I've got the point negative 1, negative 1, negative 2, negative 2, etc. So this negative out in front of the function flips it across the x-axis. On the other hand, this negative inside the function flips it across the y-axis. And what I like to think about for this one, so for this first one, all the y values became the negatives of what they were, right? I took the same function. I took the same function over here. And all that happened was every y value became the negative of what it would have been before. Right here, well, in fact, I picked different values, of course, right? But here I picked x equals 3, I got y equals 3. Here if I plugged in 3 for x, I'd be getting negative 3 for y. On the other hand, when we flip something across the y-axis, what's going to happen is to get the same y values, we're going to need to change or reflect the x values to the negative of what they were. So in the previous one, right, we plugged in 0 for x and got 0 for y, 1 for x and got 1 for y, 4 for x and got 2 for y. Here, we can't do that. If I plug in 4 for x, I'm going to have a problem. Square root of negative 4 is undefined, not real. Here I have to plug in negative 4 for x. So if x is negative 4, y is going to be the square root of negative 4, which is going to be positive 2. And if x is negative 1, y is going to be the square root of negative 1. So all my x values are the opposite sign as they were before to produce the same y values. So I get 0, 0, I get negative 1, 1, I get negative 4, 2, Negative 9 comma 3. Ooh, and it doesn't look great because it didn't drop it well. I also remind everyone that Desmos is a very good tool for seeing things like this. I think it's kind of lovely. You can totally. Also, please do fill out the attendance form. It's on Canvas. I forgot to bring the things with me, so you fill it out, please. But it's kind of cool if you do like the square root of x, and then you just put a minus sign on it. Like, oh yeah, I can definitely see right how it just flips over there like that. And if you want, you can even grab yourself a table and be like, okay, that makes sense. Let's get a few more values here. 1 second. And then if we change this to a negative x, then we can see kind of a flip there. So I think that's useful. Question?
How do you know when the negative sign is outside the function or inside?
That's a good question. I would say practice and experience are definitely good things to answer that question. But really, so it depends what you're thinking of the function x. So this function here, I was like, oh, I think the absolute value function. Oh, sorry, apologies. This function here, the negative absolute value of x, I'm thinking, well, I'm thinking of the absolute value function, which goes like that. And then I'm taking the negative and it's out in front of the function. So I've kind of, when I say in front, I guess what I mean is here I've done the absolute value of x first and then taken the negative of that after. On the other hand, for this function, I'm doing the negative of x first and then taking the square root of that. So the square root function is happening after I have done the negative of x. And it really is kind of vital that we do the order of operations correctly to kind of see which is which. So we definitely have to be, oh yeah, here you do the negative before you do the power. So it's the negative first and the square root second. So I'm doing the negative inside the function before I actually apply the square root to it. It does take practice. Question? Yeah, sorry.
So you're not actually taking the square root of a negative number?
We're right, because we can never actually get square root of negative numbers. So what we're doing here, when I plug in -4, which is not enough room on this page, I'm taking the square root of, well, I'm plugging in -4 for x. So it's -4. The -4 is +4. So I'm really taking the square root of +4 and getting +2. So but you're totally right. I'm never taking the square root of a negative because I can't. It just happens here that my input is a negative number, but then I take the negative of that to make it positive, and then we take the square root and things work out as they should usually. So we're modifying the input. Yeah. Let's look at some more examples. So in the same sort of way as before, where we multiplied by a negative either inside or outside of the function, now we're going to add a number inside or outside the function. And what we're going to see is the same kind of result. When you add a number outside of the function, it's going to shift it vertically. And you can think about this, we're just going to be adding this number d to the y values. So what's going to happen here is this is going to shift vertically. And you can say, I would say it's going to be up if d is greater than 0, down if d is negative. Adding a number inside is a little counterintuitive. This is going to shift it horizontally, but kind of the opposite way you might imagine. So if we add on the inside, it's actually going to shift it to the left. So it's going to be left if that number is positive, right if that number is negative. And here's the way I like to think about it. If we're adding 1 on the inside, x now has to be 1 less than it was before to get the same y output. So let's make a little table here. So normally, if I was plugging in like, say, Yeah, sure. I would start with 0 and then square root of 0 would be 0. But now when I plug in 0 here, my input's bigger than it was before. So I'm getting square root of 1, which is 1. What I'm trying to find is, well, I kind of like this to be the same as it was before. So instead of the square root of x, my x values need to be 1 less than 0. And I feel like this table is not exactly what I wanted. So what I really want you to see is this. So what kind of values do I want to take the square root of? Well, nice. Now you can take the square root of any positive number or non-negative number. We usually kind of say it was 0, 1, 4, 9, because those are easy to take the square root of. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Okay, but now here's the point. If x plus 1 is 0, what does x have to be? X had to be negative 1. So that when you plug in negative 1 for x, negative 1 plus 1 is 0. And if you want x plus 1 to be 4, x had to be, sorry, if you want x plus 1 to be 1, x had to be 0. If you want x plus 1 to be 4, x had to be 3. If you want x plus 1 to be 9, x had to be 8. So the idea is, look, normally, if we were graphing just x versus the square root of x, you would pick those values, you would get these values. But now, since the x values have to be 1 less, well, all the x values are 1 less. Or in a lot less words, we're taking this graph and we're shifting it 1 to the left. All the x values are 1 less than they were before. So here's the intermediate step to graph this thing. I always hate putting more than one graph on here. So we're going to shift this 1 left, but then we're going to add 4 and shift it 4 up. So I'm going to think of that point right there as my starting point. When I plug in negative 1 for x, I'm getting 4 for y. I shifted 1 left, I shifted 4 up. And that's the whole, I mean, it's not the whole picture. That's kind of the biggest piece of the picture here. We know what the graph looks like. We've already graphed a square root before. It has this kind of up and to the right shape. So we're taking that shape and just starting right here. It goes up and to the right. And maybe I would have plotted a few more points, like if I plugged in 0 for x, I'm going to get 5 for y. If I plugged in 3 for x, I should get. See, so my graph isn't perfect here, right? I missed that point there. It should have been really 3, 6. Such is life. Sometimes your graphs aren't quite perfect. That's okay.
So the plus 1 in the function shifted it like 1 to the left.
Exactly. Yes. Yeah. And the plus 4 did what? Up 4. Let's look at the next one. So this one shifted. When we added 1 on the inside, we shifted 1 to the left. When we added 4 on the outside, we shifted 4 up. This next one, it's the cubic function. But before we do the cubing, we're shifting 5 which way? To the right. And we're shifting 2 which way? Down. So this one's going to go right 5, down 2. So we're going to be over here 5 over and then down 2. So I'm thinking about that being kind of like the origin of this new graph, right? Usually, and again, the cubic graph is not my best graph, just point out. This one would usually kind of do this kind of deal and go through the points -2, 8, -8, and -1, 1, and 0, 0, and so on. But now this one's going to do this sort of thing. It's going to look like this. So taking that graph, that previous cubic graph that, again, we all might agree I didn't do a terrible job, but it's not for this job. And I've shifted it exactly 5 over and 2 down. And then it just looks the same, just over 5, 2 down. Question?
Yeah. This one's dumb, but
No, no, no.
how are we, like, maybe I'm not paying attention. How are you actually graphing? Like, I don't see the point that you're like
Right.
these points. I'm like,
No, you're totally right. How am I graphing? So what I'm doing is I'm taking the graph that we had before. I'm taking the square root graph that I know looks like this. And I'm saying I'm moving it over 1 to the left and 4 up. And then the whole graph is getting transplanted. I'm also, and you're not wrong, I'm also thinking about the points. Right? I'm thinking, okay, I know that when I graph the cubic function before I shift it, I get the points 0, 0, and 1, 1, and 2, 8. So I'm going 5 to the right and 2 down. Instead of getting 0, 0, now I'm getting 5, negative 2. And then I'm going to kind of move over 1, and up 1. I know there's a point over 1 and up 1. And I'm going to move from that point over 2 and up 8. So that's kind of how I'm thinking about it. But the idea here really is, and the kind of the thing that people are going to expect in the future, is that you kind of know these basic graphs like the square root graph, the quadratic graph, the cubic graph, and then that you're able to transform them is what this is called, by either shifting them or reflecting them. There's one other type of transformation as well that we're not talking about today, but that's the kind of idea.
Is that supposed to be a D versus X, the greater sign?
I'm sorry, say that one more time.
Is it supposed to be a D greater than 0 or 0 greater than 0?
That's so this one right here.
One over. And the other one's the very.
Oh yeah, those are both D's. Yeah, that's a D greater than 0. That's a D less than 0. Sorry about that. Okay. Do a couple more examples. So, and I'll try and be a little more explicit about what I'm doing here. So this negative absolute value of x minus, in fact, yeah, need more graphs. Well, so here's how I'm really thinking about this. Negative absolute value of x minus 2. I'm taking my absolute value graph. So I'm going to draw a bunch of graphs on this one, and then we'll just look at the final results. So here's my initial absolute value graph. And usually we try and work from the inside out, meaning if I look at the first kind of thing that happens to x, I'm subtracting 2, which means I'm going to shift it 2 to the right. X has to be 2 bigger than it was before, right? In the previous absolute value function, if I plug in 0, I get out 0. With the absolute value of x minus 2, I have to plug in 2 to get out 0. So x had to be 2 bigger than it was to get the same y values. So here's my absolute value of x minus 2 function, which is just my absolute value of x function shifted 2 to the right. Questions so far? It's okay to ask questions. I want to hear them. Okay. You could also be thinking about plotting points, right? So when I think about an absolute value graph, I think of the points, and they're not hard points, 0, 0, 1, 1, 2, 2, 3, 3, etc. And then negative 1, 1, negative 2, 2, negative 3, 3, etc. For this red one, I'm thinking my x value is 2 bigger. So now I'm getting 2, 0, and 3, 1, and 4, 2, and 5, 3. What's this negative going to do for me? It's going to flip it down across the x-axis. So I'm going to take this red one here and flip it down. And honestly, if you graph this and just have the right shape and the right intercept here at 2, 0 and 0, negative 2, that's enough. And no one's checking all your points. They just want to see that you kind of see the shape of it and have it going the right orientation. Yeah.
I guess that's my question. Like, for the credit, we're just trying to get the shape, not. That's what I was like.
That's a fair. No,
I was like, when are you doing the math, the actual point?
Right. I'm not doing a lot of math. No. So if someone said to graph something like this or this or this, and to be very specific about your intercepts, which is often what people are looking for, well, then if I looked at this graph, I'd be like, well, there's clearly a y-intercept. When x is 0, y is going to be 5. And there are no x-intercepts, right? If you set this equal to 0, there's no. Then we can see that from the graph. This one, on the other hand, right, it's a bit more work. If you wanted to find the y-intercept, you set x equal to 0. You're going to get y equal to -5 cubed. That's -5 cubed minus 2, which is -125 minus, which is -127. I didn't graph it because it's way too big to graph, but there still is a y-intercept there. Same idea here, right? You could find the x and y-intercepts. Y-intercept, you would set x equal to 0. You would get y equal to 2. Sorry, -2. Apologies. You set for the x-intercept, you'd set y equal to 0, and you would set that equal to 0, and you would get x equal to +2. I'm not really looking for you to do that here, but you are right to ask, because in the future, someone may be like, yeah, I want you to graph this thing and show me all the important points. But for right now, that's not really what the focus is, but it's definitely fair to ask. All right, another graph. So again, here's what I'm doing. I'm thinking of my square root graph. So here's my, what we often call the parent graph. So there's my parent graph. You don't have to graph all the intermediate graphs. I'm graphing them to kind of help see what's happening here. And then we're working from the inside out. So the square root of -x is going to flip it across the y-axis. So here's the square root, and which I'm never good at drawing. That's all right. So here in red is y equal to the square root of -x. And then we're going to shift it which way? Up or down? Up by 3, because we're adding 3 outside of the function. So we're going to shift that up 1, 2, 3. So the y-intercept is 0, 3. The next point to the left would be -1, 4. But then I'm really just going to try and draw it the best I can. Which is maybe not so good. We flipped it across the y-axis, we shifted it up, and then we just drew the kind of typical square root shape in that orientation. Yeah, so if I were trying to show work for a question like this, I might show all these steps.
What is it fine? Just to write down, like flip.
Yeah, no, I think that'd be great to write down, like flip across the whichever axis is the correct axis, and then shift up or down, whichever, or left or right. Yeah.
Do you shift after you do the?
That's an excellent question. That's the next page. Yeah.
Like for showing work, we just draw it like it's not really.
Yeah, I mean, yes, I would say draw it, try and maybe just like, I think Christian's suggestion is a good one. Say what transformations you have done. That it's there's the flip.
It's kind of like on the side of the graph, one.
Yeah, right. Like,
Two flip.
right. But and definitely you want to say the direction. So up, down, left, or right. If you're shifting, which way you're reflecting. So across the, you either say across the y-axis, or you can say horizontally, or you can say across the x-axis, or you can say vertically. If I saw another hand over here. Olivia, did you have another question? No. So yes, what order do you do things in? This is actually what I think is probably the hardest part about this, is the knowing the order. So horizontally, you want to do the shifting before you do the reflecting. Vertically, you want to do the flipping before you do the shifting. I know, it's kind of a pain. There are other ways to do so for me personally, the vertical stuff is not that bad. Vertical is usually pretty easy. Like, oh yeah, I'm going to flip it and I'm going to shift it up or shift it down or whatever. It's the horizontal that always screws me up. I have to always think about it every time. I'm like, okay, so here's what we're going to do. We got a square root of a -x plus 2. So I'm going to do the shift first. I'm going to shift it to which way? I'm adding, I'm shifting it to the left. So first, left by 2. Second, reflect across the y-axis. I'm going to draw the first. So here's my first left by 2 graph. So here's the square root of just x plus 2. And I'm going to reflect that whole thing across the y-axis. So this point that is at negative 2, 0, where's that going to reflect to? To positive 2, 0. I'm reflecting across the x-axis, sorry, I'm reflecting across the y-axis. All the x values become the opposite sign. So the point negative 2, 0 becomes the point positive 2, 0. And this one would have the point negative 1, 1. We're going to get the point positive 1, 1. Sure. So that's what our finished result looks like. We shifted the whole thing left by 2, and then we reflected the entire thing across the y-axis. So this point reflected over to there. And this point reflected over to there. If you draw both the graph and its reflection, not that you should do that, but if you do draw them both on the same coordinate system, they should look like a mirror image of each other. Right? There should be definitely symmetry when we look at that. The mistake I've seen people make in the past with this kind of thing is they want to kind of do the reflection and then the shifting. So the graph, the most common mistake graph that people kind of do when they graph this is they end up graphing like this, where they shifted 2 to the left and then reflected about the line or about that point, negative 2. That's definitely not the right graph there. This would be y equal to the square root of negative x minus 2. Okay. We could plot some values. That's also a helpful thing to do, right? You don't, so I'm trying to show you the way that I think about graphing these because it's meant to be the most efficient. If you're not trying to spend a ton of time graphing this thing, you're gonna be like, what is this thing just look like? But we can also plot some points. I could say x is now 0, seems like a good thing to pick. But if x is 0, what do I get for y? Well, I get the square root of 2, which is fine. It's a real number. It's just not one I'm used to plotting. I can also pick x equal to 1 and get y equal to the square root of 1, which is 1, or x equal to 2 and the square root of 0. And that's as big as x can go, which is helpful for me to know because then like, oh yeah, it makes sense that 2 is as far right as this graph goes, and then it has to kind of go to the left. So I can pick values like negative 1 and get the square root of 1 plus 2, which is the square root of 3. I can pick negative 2 and get the square root of negative 2 plus 2, which is the square root of 4. So there are definitely points we can plot if we want to do it that way. It's just, it's not the most efficient way to do it. So again, horizontally, you want to do let me look at the word so I say it right. You want to do the shifting before you do the reflecting horizontally. On the other hand, when it comes to vertically, we wanted, so yeah, it's a little, so I will say, as is typical with graphing stuff, the horizontal things are always a little counterintuitive. Because if I looked at this, if I was just thinking about things the way I usually think about them, I'd be like, oh, you do the shift first because the negative hits the x before the plus 2 hits the x. But it's just, this is the way that I think is the easiest to see it. If you have a different way of doing it, that's also really okay. But I've tried to do this different ways and I always end up screwing it up. So this is the way I'd be like, oh yeah, you do the shift first, you do the reflection second horizontally, and you're safe. That's what I would say. But for vertically, you do want to do the reflection first. So negative absolute value of x plus 3. First, we're going to do the reflection down. Here's my negative absolute value of x. I didn't graph the parent graph. I guess I could have. But we know so the idea is like, oh yeah, absolute value of x just looks like this, and we're just reflecting it down so it looks like that. And then the plus 3 is going to move it which way? Right, like the movie that makes you cry. Up. up 3. So we're going to go 1, 2, 3 up, and it's going to look like that. So we could write reflect vertically. And then, and I really should number them. And then shift up 3. We could also plot some points. It seems unnecessary. We totally could, right? If you plug in 0 for x, you're going to get -0 plus 3. You plug in 1 for x, you're going to get -1 plus 3. And really, it doesn't matter if x is positive or -1. You're going to get the same y value. And if you write for this absolute value one, it doesn't matter if x is positive or -2, you get negative absolute value of 2 plus 3. Well, the absolute value of positive or -2 is going to be 2. So you get -2 plus 3, which is 1. And we totally have those points, 2, 1, -2, 1. So you can always fall back on plotting points, but the idea really is to have a good idea or impression of kind of how these basic graphs look, and then just be shifting them left, right, up, down, reflecting them vertically or horizontally. So I'm missing a page. Nope, I'm not. Okay. So a couple more graphs to be aware of. We're not going to shift these. We're just going to look at them. So we've got 2 graphs. We've got y equals 1 over x. We've got y equals 1 over x squared. So I'm going to plot a few points. If x is 0, the 0 is a bad idea. If x is 0, we're undefined. Okay. If x is 1, y is going to be 1 over 1. I can plot that point. Okay. If x is 2, y is going to be 1 over 2. There's not really any simplifying there. I guess you right. And I'm not going to plot a whole lot more points because things are going to get very close to 0 very fast. Right? If x is 3, y is going to be 1/3. And already I'm getting kind of right. It's not going to be easy to make graph. So what I can see here is that as the x values get larger, the y values are getting smaller. So it's going to look like this as we go to the right. Closer and closer and closer to 0. Now what happens as x gets smaller? X is like a small positive number, like 1/2. What's 1 divided by 1/2? 2. So if x is 1/2, the y value is 2. And if x is a smaller number, like 1/4, y is going to be 1 over 1/4, which is 4. And what happens is as the x values get very, very, very close to 0, as the x values get very close to 0, the y values get very, very, very large. Larger and larger and larger without bounds.
But they never fully touched it.
Right, it never touches the x-axis. We have what's called a vertical asymptote. So this graph definitely has a vertical asymptote at x equals 0. Now that's not the whole graph because x could also be negative. And we get the same sort of thing happening. If x is -1, 1 over -1 is -1. If x is -2, the y value is -1/2. If x is -3, the y value is -1/3. And it gets closer and closer and closer to 0 as you move further and further and further to the left. And then as the x values get smaller, like -1/2, -1/3, -1/4, the y values get very, very negatively large. So we could plot more values. Like you could say, okay, if x is -1/3, y is going to be 1 over -1/3, which is -3, and so on. This is a very standard graph. 1 over x looks like this. It goes down and then it has a vertical asymptote, and then it comes back down like that. There's something else I want to say here. No, I guess not. Questions about this graph? The thing I would encourage you to take away from this particular graph is the idea that when you have 1 over x, or a fraction in general, if the denominator is large, the overall quantity is small. 1 divided by a large number is a very, very tiny number. 1 over 1,000 is 1 over 1,000. That's 0.001. Whereas if you divide by a very, very small number, the quantity gets very, very large. 1 divided by 1/1000th, well, we flip and multiply. 1 times 1,000 over 1, which is 1,000. So as x gets very, very close to 0 here, the y values get extremely large. And it doesn't matter if x is getting close to 0 from the right-hand side, where x is positive, or from the left-hand side, when x is negative. If x is negative small number, you're going to get 1 times 1,000 over negative 1, which is negative 1,000. So if x is very, very, very small but negative, you're over here, and the y values are getting extremely negatively large. Okay. One more graph. It has a similar shape, but not quite the same. Let's make our graphing a little bit easier. Well, because we can here. X could be 1, and y would be 1 over 1, or 1 over 1 squared. But it doesn't matter if x is positive or negative here. Because if x is positive 1, y is going to be 1. If x is negative 1, y is still going to be a positive 1, because a negative number squared is the same positive number. And we can kind of see that's true for anything here, right? If y equals 1 over x squared, for every positive and corresponding negative value, the y value is going to be the same. So if x is plus or minus 2, y is going to be 1 over positive or negative 2 squared, which is 1/4. And right, as the x values get larger, the y values get smaller. 1/4, 1 over 4 squared is 1/16. So we get some values there. This one's even harder to draw because things get small so fast. But all the values are positive here, right? The y values, whether x is positive or negative, the y values are themselves positive. And then as the x values get very, very small, if x is 1/2, for example, 1 over 1/2 squared is 1 over 1/4, which is 4. And that would be true whether x was positive or negative. So this one also does the same sort of thing and has a vertical asymptote at x equal to 0. The graph never touches x equal to 0. I feel like I'm spelling that very wrong. Something else to say here? I guess not. So these are some other standard graphs. All of these ones before we shifted them or selected them are considered like standard graphs that everyone is kind of like, oh yeah, we know this graph, we know this graph. I feel like there's a section in the pre-calc or when you take calculus next quarter, there's usually like a section in the first chapter. It's like a catalog of essential functions. Here's a list of like the 10 different types of functions. You should kind of know that what they look like and be able to shift them or reflect them or stretch them, which we'll talk about next time. All right, that's all I've got to say. Oh, sorry, there was a question there. Oh, good question. Yeah, excellent. So let me just say one thing. What's the domain and range for those last functions? Good question. So for this one, the domain is everything except for x equal to 0. So you can say all reals except x equals to 0. Or in interval notation, it'd be negative infinity comma 0, parentheses because we don't want the 0, union 0 to infinity. And for this one, the range would actually be the same. Also, everything except 0. I do want to stress the point there that the range is all the possible x values and the range is all the possible y values. For the second one, the domain would actually be the same. the fast but kind of less, the less rigorous way of writing this is the domain is x not equal to 0. Really, we mean all real numbers except x equal to 0. So we would really write this as. And then finally, the range for this last one, y has to be strictly positive for this last one, which we could write as everything from 0. Good question. Thanks for that. Appreciate it. Yeah, question.
So X number goes, X number goes to 0, but what about the Y?
The y never goes to 0 either.
Okay.
So, and here's how I encourage you to think about it. The y is equal to 1 over x squared. Can 1 divided by x squared ever actually equal 0? No, it can be really, really super small. Right? X could be 1 billion, and 1 divided by 1 billion squared is extremely very small. And some calculators might tell you that's 0 at some point because you've gotten too close to 0 for them to say it's anything else. But the answer, Danny, you're right, is no. This can never actually equal 0 if you're plugging in a real number for x, because it's always just going to be 1 divided by some very large number. And what I usually like to think about is whenever you have a fraction or a rational expression, something divided by something else, it can only ever equal 0 if the numerator can be 0. And since the numerator here is always 1, it can never be 0. Good question. Thank you.